Hello everybody, welcome to this webinar and thank you for spending some time with us today. This is Ertem Esener. I am a research scientist and the coordinator for research collaboration and industry relations at ADSC. So let's start with the introduction of ADSC and its TSCP program. So University of Illinois Advanced Digital Sciences Center was established in 2009. Supported by A-STAR until 2017. And at that point, we became NRF's CREATE program. So our research in cybersecurity and analytics is led by faculty from the Granger College of Engineering from the University of Illinois. So to date, we have 8 Illinois professors from electrical and computer engineering and computer science faculty and 24 full-time researchers based in ADSC. The research projects range from basic to applied research, and ADSC has published more than 600 publications in international journals and conferences, won 28 Best Paper Awards, filed more than 2 dozens of technology disclosures, with 12 filed or granted patents since 2009. So our contributions to the innovation economy is with 12 startups since 2009, and 23 technology licenses to both local and US companies to date. ADSC's leadership is comprised of faculty from the University of Illinois who spend significant amounts of time at ADSC directing research and interacting with NRF and with industry leaders in Singapore. So in total, 8 UIUC faculty participate in the CREATE program. Program also supports half a dozen or so support staff, as well as 2 dozen research or staff scientists and engineers. In 2017, ADSC formally partnered with Singapore University of Technology and Design to continue research on trustworthy and secure computing systems for critical infrastructure, using energy systems as a concrete driver for this research under the NRF CREATE program for a trusted and secure cyberplexus. The focal point of the CREATE program is to provide better cybersecurity for the electric power grid. The basic idea is to develop an overlay network whose devices are hardened against attacks, whose policies are designed to improve the cybersecurity of the network as best as can be done under logical and financial constraints. A number of new technologies have been developed to support this vision under these 4 interlinked thrusts, so addressing central challenges in the development of the TSCP platform. So trustworthy system architecture, technology of trust, standards validation and verification, monitoring and analysis. Now let's briefly see the contents of them. So the first question is, why these trusts in order to confidently achieve an increased protection of a system of critical infrastructure, and that it is trustworthy and secure. So Trust 1 deals with architecture. Where are the critical and strategic placement points for the TSCP appliances? What sets of security policy should be enforced to maximize security protection without violating any real-time system constraints? Right, the picture on the right is an augmented diagram of an electric power testbed at SUTD. So the outcomes of Trust 1 is shown as the circled TSCP blocks as bump-in-the-wire devices inserted into the electric power testbed. Trust 2 is technology of trust. What are the new trust technologies needed to support real-time application of policies for devices and communications? As seen on the right as the edges connecting the TSCP appliances circled there. Trust 3 is standards validation and verification. It's like, where is your proof certificate? Are you one of the trusted third-party applications authorized to access the system? How are the TSCP appliances hardened and have the highest assurance that they are secure? Trust 4 is monitoring and analysis. So what is happening at system level? Is the system under attack? Or is it showing signs that an attack is underway? So in summary, ADSC cybersecurity research conducted under the TSCP program achieves increased protection and resilience for critical infrastructures, which may consist of legacy components in a transparent manner with no need for change and upgrade to legacy components. Our solution, as you can see in the diagram, is to be an overlay network that is trustworthy and secure for protecting critical infrastructure. I brought some backup, so Dr. Daisuke Mashima, Dr. Xin Lu, and Dr. Yao Chen to later elaborate on some of these, as well as an example of ADSC's externally funded projects. But first, I want to start with a toy example on how one can collaborate with us, ADSC. Let's say our partner here is after a message authentication scheme. However, either it is out of their expertise or their requirements are rather unusual. So what are we after? We need to guarantee source and message integrity to prevent some attacks in critical multicast messages. Okay, so IEEE guidelines suggest the use of RSA. It takes around 8 milliseconds to sign a message with a device that costs $200 in terms of processing power. Okay, we need to receive a message within 2 milliseconds after it's being sent. So we do not have that much time. Okay, cool. Let's say we use the other state of the art then, which is ECDSA. Even better, let's do most of the operations before the message is even known, right? It's called the offline time, and it takes around 4 milliseconds. Then all we need is around 2 milliseconds to both sign and verify after the message is given. And we can send one message every 4 milliseconds. How is that? Well, even if we could work with the full 2 milliseconds taken by it, it makes around 250 messages per second. Very limiting. See, we need around 4,000 messages per second. Okay, now we need to think a bit because like these were the state-of-the-art methods, but they do not work. So clearly we need to sacrifice from somewhere to satisfy the said requirements because there is no free lunch. So we need to figure out what we can trade. So in modern gigabit connections, we sure can sacrifice from the communication department. So that is good, but so maybe we can try something around one-time signatures. Okay, then let's see where we can sacrifice from while satisfying above. What is the entropy of your messages? So here we are digging a bit now. And also, how many different messages may there be for the important secure kind of messages? Maybe just warning messages or critical commands. Maybe there aren't that many. So we do a few digging. So we figure around 4 billion or so different messages, such as alerts, commands like circuit breaker, unexpected readings, their values. But one is not considerably more likely than another. So we could try something with prediction or prioritizing. If so, regardless, we see that the entropy in these messages is around 32 bits, right? Then we can assume the messages are rather short. Yes, we can do that. Okay, now we need to think a bit again. So benefiting from small messages to satisfy these is a great idea. But variations of one-time signatures like a straightforward and efficient extension to benefit from small messages. And they sure are not secure by the, they are sure secure, but they are not enough to satisfy the performance requirements. Cool, so how about the network, say bandwidth? So yeah, our system supports gigabit connection. Cool, then we can sacrifice from communication really to gain speed and message frequency. So we will work on this. Most importantly, we need to benefit from the shortness of messages. And in most systems, the most critical and time-stringent messages, such as alerts, urgent circuit breaker, or shutdown commands, are the shortest of them all. Sometimes a few bits of information, such as an emergency code. So the authentication should be the shorter, the faster. Therefore, variable message size is a key. But we cannot do it like public key signature schemes then, where the message has to be hashed, so the shortest message to authenticate is 256 bits. Let's also don't forget we have to support multicast messages, right? So one source, multiple destinations. And of course, there are others that we need to keep in mind, such as legacy compliance, ease of integration, or low-cost devices, and so forth. So we want to achieve that the message authentication incurs very minimal delay, right? Even so that it is virtually unnoticeable. So we achieve this by performing all the expensive computations before the message is given, both at the sender and receiver sides. That is not enough, but it's a start. The requirements we just learned from our partner were for IEC 61850, which is the communication protocol for electric substation automation. The techniques we developed sure is also applicable to any machine-to-machine communication setting with stringent delay requirements. Yet, this is our playground now. Indeed, many digital systems and protocols rely on low latency, high throughput communication. For example, in the case of IEC 61850, thousands of messages per second, and the tolerable delay is less than 2 milliseconds. So in particular, with IEC 61850, Goose protocol is used by intelligent electronic devices, IEDs, in a substation to share status and events. Goose is a publisher-subscriber protocol, so a source multicasts over Ethernet, and the subscribers receive and process the message at their will. So IEC protocols are not protected from false packet injection attacks, so a malicious actor can send harmful messages and threaten substation security. For example, a compromised IED or an adversary with access to the network can generate goose frames with manipulated values. A compromised IED can also impersonate another IED, sending forged goose frames with a fake source ID. So there are many existing solutions for message authentication, as we discussed a bit. So digital signatures are widely used. They enable verification of source message, like source and message integrity. And they also offer non-repudiation. They are inherently suitable for multicast setting because any entity with the knowledge of the sender's public key can perform this verification. However, the drawback of digital signatures is the expensive computations, such as modular exponentiation, elliptic curve, scalar multiplication, and so on. So these computations introduce high latency for signing and verification of messages, especially on resource-constrained IEDs. So for example, IEC standards suggest the use of RSA for message authentication, but signing a message with RSA incurs an overhead too large to be tolerated by the very standard itself. Another possible solution to implement security with the latency constraint would be to use a lightweight message authentication code, such as an HMAC. This would work well in the case of unicast, right? But in the case of multicast, a separate message authentication code needs to be calculated for each recipient. And this increases the computational load at the source linearly with the number of recipients. Another limitation of such symmetric key-based solutions is the lack of non-repudiation, of course, which may be required in industrial control systems involving multiple management domains. There is also the concept of performing pre-computations, shifting expensive computations to a phase before the message is given, so an offline phase, so to say. So online-offline signatures and ECDSA with pre-computation enabled perform some of the expensive computations before the message is given. But even these state-of-the-art schemes perform certain expensive operations in their online phase. To address these challenges, we propose a new model for digital signatures called less online, more offline signatures, so LOMOS in short. In LOMOS, all expensive computation are to be done before the message content is decided. So LOMOS can convert any digital signature to support pre-computation and preserve PKI properties such as third-party verification and non-repudiation. In conventional digital signatures, on the left here, the signing process starts only after the message is given. The message is decided, then the source signs the message in what is called prove here, or sign. The source then sends it along with its signature to the destinations, and then the destinations perform verification only upon receiving the message to prove. So this proof procedure involves expensive operations. In Lomos model, the source should perform all expensive operations in the setup procedure here, which is before the message is known. So the type of computation here depends on the converted digital signature scheme. One other unique property of Lomos is that the expensive part of verification should also be done offline. So therefore, before the message is given. This is done by introducing this verify setup step procedure in the online phase, in the offline phase. Since the source performs all the expensive operations in the setup, online signing of Lomos is only for memory reads and assembly. Online verification only involves inexpensive cryptographic functions, such as conventional secure hash computations, for instance, SHA-256. We also developed a construction for this Lomos model using authenticated data structures and provable data possession literature. So now a few technical slides will follow, but please keep up with me because the performance results will make more sense after we see what is going on. I'll try to keep it as high level as possible. So in this construction, we use a tri-leaf tree. The tree is built by the source in the setup procedure to generate proofs for future messages. So this is an example tri-leaf tree of length 8. Each bit of the message is represented by a leaf node that holds 3 nonce values each. 1 for 0, 1 for 1, and also 1 for the break bit, represented as Bs on the tree. Hence, it's called a tri-leaf tree. Breaks are introduced to prevent concatenation and truncation attacks. So a good analogy for the break bit would be from analog radio. When communicating with an analog radio, the users often start and end their speech with the word stop or break in that matter to enable the receiver to verify that it heard the full message. So the idea is similar here. Now I will take a few slides to go over the procedures of Lomos TT, so we will see why it works. Here is the setup. So the prover builds this tree and signs its root, which is the private key, using the private key of the converted digital signature scheme. The prover keeps the tree to itself as the private metadata, then sends the public metadata, which is the root value and its signature, to the verifier. So where the verifier verifies the public metadata with the converted digital signatures verify algorithm and stores the said public metadata, which is again the root of the tree. So it keeps the root. Okay, now we are ready to prove some later messages. The prover knows the root, verified it, and waiting for future messages. Each time the source generates a message, the prover will collect the necessary values from the tree that are to be used to compute the root hash value. We will now see how and why, but just to emphasize first, there is only memory reads during this operation, right? After the message is ready to be sent. So the proof of a message consists of 1 nonce and 2 nonce digests per leaf node. The proof also includes the values stored in the siblings of all the nodes on the pad from the leaf node to the root. So for message 1 here, for instance, which is 0 and 1 only, 2 bits for the sake of example, these circled values from the tree are included in the proof. These values allow the destinations to calculate the root using the selected hash function in this way. Each step, children's hashes are calculated to find the parent's hash value. So again, there is no computation at this step, only memory read and assembly performed by the source in this procedure. So let's go back. The source collects all these values and send them as proof. And verify is simply getting the values, hashing them together according to the message, and comparing the result with the stored public metadata. And that's all. So let's shortly visit why it works. So the nonces are created and revealed to none other than the prover. When the corresponding nonces of one of every tuple are revealed, the verifier is confident that the proof is sent by the same source that signed the root. So if an adversary can find a nonce, its value, by knowing anything just other than the nonces themselves with non-negligible probability, then we can break the preimage resistance of the set hash function, right? Because we find the input with only knowing the output. So if an adversary can find a different value to replace any of these circled ones, right? Again, with non-negligible probability, that will end up with the root's hash value. Then we can break the second preimage resistance and hence the collision resistance of the set hash function. So given that we employ a secure, right, collision resistant hash function, this whole thing works. So in theory, it should be fast and frequent, but let's see what we achieve with the implementation. So here is the chart comparing our implementation with different inputs to the mainstream solutions, right? The supported message frequency depends on the setup procedure, namely the time spent at the setup and the messages that can be supported with one setup. So of course, the smaller the message, the better the message frequency support. And at and beyond messages of 256 bits, the performance is roughly the same in all steps of this, since any message longer than that can be hashed into a 256 bits digest. Here is the targeted 4,000 messages per second. So for messages shorter than 16 bits on average, it is possible. So 16 bits here is not the upper bound for a message size, but the average message size. Now let's see if the proof and verify can be fitted into mostly already occupied 2 milliseconds threshold. Since the proof is only memory reads, it's a matter of microseconds. But other solutions at this stage are not that slow either. But the verify, on the other hand, we see a difference. Since the construction only involves cryptographic hashing and no expensive operations at all, the execution takes really, really short time. And beyond 256 bits, the performance remains roughly the same. And for short messages, where it shines, it is well below the required threshold. Okay, so some important branding, the acknowledgement, because without create, none of these is possible. Maybe for the question and answer, let's again leave it to the end of the whole presentation. But first, we said there are branches under our create program. So the work we just briefly visited aligns with Trust 1 and 2. So Xin and then Yao will briefly tell us what Trust 4 is about from their different perspectives. And after them, Daisuke will give us an example of one of our externally funded projects. So I will soon pass the mic to my fellow scientist, Dr. Xin Lu, who is online now, and he will tell us about ADSC's recent efforts on AI-based solutions to solve the cybersecurity and anomaly detection problems in cyber-physical systems like power grids, train systems, and so on. Dr. Xin Lu has been leading the efforts in this direction under Trust 4, as well as other external fundings. So Xin?
Okay, thanks, Artem, for the introduction. Okay, Artem, can you go to the next page? Yeah, thanks. So today, I'll briefly talk about our work on the cybersecurity in cyber-physical system detection, assessment, and mitigation. Next page, please. So as we know that by integrating the information and communication technology, the critical systems are transforming into the cyber-physical system. However, whereas the ICTs can improve the system performance, it also incurs the cybersecurity risk. To date, the security of this critical system has largely relied on the isolation from the public network through the air gap or the firewalls. However, the isolation is questionable due to the insiders or the stepping stone attacks. So once the attackers breach the isolation, they can launch the powerful data integrity attacks similar to the Stuxnet. So motivated by recent security incidents, we have been studying different types of cyber attacks in cyber-physical system. So today, I will briefly introduce one type of attack, which is a delay attack, its detection and impact assessment, as well as mitigation. Next page, please. So for the delay attack, it can be launched by compromising the control command transmission. For example, by compromising the router, then the adversary replays the previous commands, then all the subsequent commands will be delayed by certain time slots. So although the delay attack is very easy to launch, it can be very harmful to the system. For example, for the power grid illustrated in figure 1A, if we delay the attack, if we delay the frequency control command, the ADSC command by certain seconds, it can cause the system frequency deviation. And in the worst case, the system will crash. So the goal of this work is to detect whether the commands are being delayed as early as possible. And if the delay attack appears, we need to characterize the length of the delay. So here we mainly face 3 challenges. First challenge, the mathematical model cannot accurately model the complex CPS system, whereas the simplified or inaccurate models degrade the detection performance. Secondly, we need to have a real-time analysis to figure out the attack before it causes damage in the system. Lastly, the long input sensor stream can lose information from the past. The traditional deep learning approach, like the long short-term memory, are not suitable for the long data input task. Next page, please. So to overcome all these challenges, we proposed a multifunction hierarchical long short-term memory-based detection framework. So the input of this deep learning model is the simulator data stream. And then figure 2 shows the structure of the deep learning model. So in the LSTM layers, we have 2 levels. These 2 levels work together to deal with the long input data. And the dense layers contains 2 parts. First part is a classification module, which is used for detecting whether the attack appears. The second module is a regression module, which is used to characterize the length of the delay in the system. So by now we have tested our deep learning framework in both the power grid ADSC control and also power plant control system. Table 1 illustrates the performance in the ADSC control. We see that our approach can achieve good performance in both the regression and the characterization compared with the existing solutions. So this work has been appeared in AI in Energy System in Smart Grid Com 2019, and also IEEE transaction on Smart Grid 2021. Next page, please. So now we have the capability to detect the attack and also know the length of the delay. Next task, we need to evaluate the impact of the attack. So when the attack appears in the system, especially the delay attack, it does not necessarily mean the system performance will degrade for sure. So when the anomaly impact is mild, even negligible, then no need to alert the system operator or schedule the specific maintenance each time due to the limited resources. Moreover, if the anomaly will be harmful to a system, we need to know how bad will it be before we can launch corresponding mitigation plan. So here in this work, our goal is to evaluate the impact of the delay attack in the CPS and then launch mitigation if needed. So here again, we face 3 challenges. First challenge, we need to use the domain knowledge to recognize the impact of in the system. Second, same as before, we need to achieve the real-time assessment before the system is damaged. Lastly, we need to ensure the system resilience by launching the mitigation before the anomaly is completely removed from the system. Next page, please. So here we propose a tandem stability safety-based approach or framework to evaluate the impact. So for the safety, we propose a machine learning-based approach to evaluate. So figure 6 shows the performance of our assessment framework. And we see that our framework achieved good performance in terms of accuracy and also in execution time. Figure 7 illustrates the performance of our mitigation plan. So we see that in 2 case studies, our mitigation can ensure that the system is stable and safe. Otherwise, the delay attack will cause the system crash. So this work has been appeared in SM IEEE Conference on Cyber-Physical System 2019 and IEEE Journal on Safety Areas in Communication 2020. Next page, please. So besides the co-funding TSCP, we also have some external funding related to the anomaly in the cyber-physical system. So currently we are working on the force data injection in frequency control and voltage control in power grid. This is an ongoing project from EMA. So also we have been working on the internal and external threats in the autonomous vehicles. This is an ongoing project with the NSOE TSS. Previously, we have been working with SMRT Singapore to identify the faulty components in the train system in the Circle Line. So this is my brief introduction of our work. Thanks.
I was muted. Yeah, thank you very much, Shin. And next up, we will invite Dr. Yao Chen. Yao will tell us about ADSC's recent efforts on accelerating the deep learning algorithms for real-time analysis and cyber-physical systems with large amount of input data. So Yao has been leading the efforts in this direction, mainly on the acceleration with special focus on heterogeneous clusters and novel FPGA-based accelerator system design. So Yao.
Okay, thank you, Artem. Can you hear me?
Yes, we do.
Okay. Hello, everyone. This is Yao, and I'm also currently I'm a research scientist with the ADSC, and I'm also serves as a coordinator for data analytics and hardware research. Can you start the next page? Okay. So today I briefly introduce some of our ongoing approaches about specifically focusing on accelerating the machine learning for the real-time detection. Next. Okay, as Shin just mentioned in the CPS system, that we are capturing more and more data and from all the different sensors and all the different nodes with different log files. And those increasing data volume that requires the acceleration for the analysis to detect the anomaly from a cloud to the edge approach. And there are also quite some new devices that are being adopted in the modern computing systems, such as CPUs equipped with new architectures and the newly deployed GPUs and the reconfigurable devices. So, and FPGA as one of the representative device for the reconfigurable devices, it provides advantages in terms of both the power efficiency and latency when compared to both the CPU and FPGA. Next. So our first approach focuses on the providing the capability to do large amount of data analysis for the cluster point of view. We deploy this on the cloud, and with the specific focus on the anomaly detection with a large amount of the data input. Here, the challenges we were facing is supporting the CPU, GPU, and the FPGA. This is the heterogeneous cluster and equipped with all these different devices so that it could be served for the different kinds of the applications. And in order to use them in an efficient way, the framework or the way we call this cluster have to be aware of the heterogeneity of all the underlying devices. And again, in order to provide a more friendly, user-friendly pattern, we also need to unify the interfaces for all these different accelerators. Okay, go ahead. So the approach we take here is designing a unified framework that manages all of these different kinds of the accelerators, which are the CPU, GPU, and the FPGAs in a holistic manner. And in addition, we also design a new runtime resource monitoring and scheduling component into this framework. And we adopt the lightweight communication backbone, so the communication between inside these big clusters between all these nodes would not be the bottleneck. And we also design all of this into OpenCL wrapper, so it could be compatible. We could use an OpenCL compatible interface and easily call all of these underlying resources. So the results are promising, although this project is still undergoing. And now we can already achieve a linear speed up with the increase of the scale of the clusters, or with the scale with the number of the nodes. And the overhead in this system is already being minimized. Okay, go ahead. And on the other hand, not for the cloud, for the edge edge scenario that we know for the big power grid system or the CPS system, we always require quite some nodes to be put on the edge for either the detection or some analysis. And sometimes we even need the bumping wire devices, but those devices are lack of computing capability. And especially when we want to execute some of the machine learning algorithms, such as the deep neural networks, they are quite a lack of the support for this. And we also want an inexpensive and easy to use hardware that can process this in case we would need to do some infrastructure change for the CPS system. So the challenges for this direction we are facing is the algorithms or the deep neural network models are way too big for the devices, and the GPU devices are actually quite power hungry. We cannot always use GPUs for the IoT nodes or for the bumping wire scenario. And in order to make them more efficient and cause low latency, we use FPGAs, but FPGAs are actually error prone, and the design and deployment of FPGA devices are quite time consuming. And again, from the model part, it's quite complicated to customize the models to own these low capacity devices. Next page, please. So here we actually take the approaches on two different directions. From the software part, we design a unique ternary quantization for this deep learning models, that we quantize all of the model weights into ternary, so the entire computation pattern would be changed. And then for the additional data to be processed, we use a fixed point quantization. This kind of the fixed point quantization is quite mature, and we directly adopted some of the existing solutions. And for the hardware part, we designed a novel processing unit, which is constructed with efficient data flow architecture. And on top of this, we designed a new instruction set that provides efficient calling and configuration of the entire data flow. So the current results are quite promising, that we use the smallest platform provided by Xilinx, which is the smallest FPGA device. And we are already being able to deliver the performance equals to, the performance in terms of latency equals to a desktop GPU, which is a 1080, and we are already 200 times faster than a desktop CPU. Okay, here's the two ongoing directions, and now we are also further extending the capability of these two directions. And if there are any interest, please contact me or Ertem. Okay. That's all from my side.
Yeah, thank you very much, Yao. So, yeah, ADSC has also been working on the design and implementation of virtual testbed, emulating smart power grid systems, which can support design experiments as well as data collection for cybersecurity and AI in the area. So Dr. Daisuke Mashima has been leading these efforts, though he is the TSCP program coordinator. Today, he'll be telling about, he's here to tell us about this. So he was leading these efforts under multiple external fundings. So Daisuke?
Hello. So thank you very much, Artem, for the introduction. Next, please. Okay, so I'd like to briefly talk about the research work on the design and implementation of the so-called cyber range, or sometimes it is referred to as a digital twin of the industrial control system for the cybersecurity research R&D. Next, please. So first, what is a cyber range? So it is, in short, it is a virtualized version of the industrial control system for the cyber security experiments. And then, so why we need a cyber range for the industrial control system? Recently, we are hearing a number of bad news about a cyber attack against our critical infrastructure. So say, for instance, in 2015, power plant of the Ukraine was got a cyber attack, and then it caused a massive power outage. And also even more recently, so actually this year, so some water treatment plant in US was attacked by the hackers, and the attacker aimed at injecting some like a toxic chemicals into the water treatment system. And so because say such a consequence of such cyber attack could be a life-threatening, so therefore we need a cyber security solution for protecting our critical infrastructure. And to do that, we need a say environment for assessing the impact of the cyber attack, as well as evaluating the effectiveness of the cyber security solutions. So that's why we need the environment for the evaluation. Of course, maybe ideal approach would be to do such evaluation experiment by using a real system infrastructure. But unfortunately, it is almost always impossible. And maybe next best solution is to create an isolated a test bed using real hardware in both cyber side and physical side. It is good in terms of fidelity, but it has an inherent limitation and also challenge in terms of cost, scalability, and also configurability. And besides, even in such an isolated environment, certain type of high-risk cyber attack experiments cannot be conducted. So say, for instance, this picture is showing one of the experiments conducted in the US, where the researchers demonstrated that the cyber-originated attack can actually destroy the physical generator device. But say such a high-risk experiment would not be approved by the operator of the testbed in many cases. So therefore, we need a virtualized environment to conduct any kind of experiments. So that's why we need a cyber range. Next, please. Okay, and in this direction, ADSC has delivered a couple of research outcomes, mainly in a smart power grid system. So first one I'd like to introduce, which is shown on the left, is a software-based substation testbed called SoftGrid. And this was developed for the evaluating our own bump-in-the-wire cybersecurity solution for the smart grid system. And to do that, SoftGrid incorporates a standard compliant cyber system as well as the power system simulator at the backend, so that we can evaluate the impact the cyber attack on the physical power system. And actually, so this setup was utilized for multiple technology demonstration in the recent past. And in another project, which is shown on the right, we have implemented a more comprehensive cyber range of the smart grid infrastructure, which includes a control center system as well as the field substation system. And this work is actually using a SoftGrid as one of the building blocks. And so this newer setup included more components which are typically found in the real system infrastructure, and therefore this system is closer to the real system environment. Actually, main motivation for us to implement this system is to develop a so-called honeypot system. So honeypot is a cybersecurity tool, and it is a sort of a dummy system to intentionally attract cyber attackers inside, so that we can collect intelligence about, say, their profile, activities, and also strategies. And that's why honeypot needs to have a higher fidelity to the real system. And to evaluate the realism of our implementation, we actually collaborated with a cybersecurity expert in Singapore to do a penetration testing using this environment. So this way, cyber range can also be utilized as a building block for the cybersecurity tool like honeypot. And also it can be used as a venue for the, some kind of cyber security or cyber attack hands-on exercise like a penetration testing. And by the way, both of the implementations are available to the public as a sort of open source. If you are interested, please go to the website shown on the slide. Next, please. Yeah, and actually, based on these experience through our real project, we found that still a challenge is a design and implementation of the cyber range requires significant effort, time, and also intensive domain knowledge both in the cyber side and the physical side. Besides, many of the cyber range or digital twin implementation available nowadays is more like a one-off solution, and it does not consider the portability and also extensibility in mind. And to address these challenges in our ongoing project, we are working on development of the technology for automatically generating a cyber range according to the user-defined models. Next, please. Yeah, so in this project, we first define the modeling framework or like a modeling language, which is both human-friendly as well as machine-readable. And this language can be utilized for the human user to characterize, define the devices and also topology of the cyber range. So then this language can be parsed by our own open source toolchain, which is called the SGML processor. So this tool interprets a model and then automatically instantiate the components or topology on a virtualized environment, such as a PC cluster or like a cloud kind of environment. Yeah, and this way, I think this kind of solution can benefit many types of users, not only researchers, but also infrastructure operator, as well as training and also education sectors. I think that's all my part. And if you are interested, please feel free to talk to us. Thanks.
And yes, thank you very much, Daisuke. That's also all from us. So we would be maybe happy to take on the questions now. I see some questions are answered via chat, but let me take them by voice. So the first question here is, would the online setup, so this is about the first part, the signature scheme, need to be repeated periodically, and can it be compromised after setup? Well, yes, so that's a nice catch. So the setup should be repeated periodically, even usually in a matter of seconds, if not minutes, because the tree itself, as we saw, can be consumed. And even if it is not consumed, still the freshness guarantee requires that kind of a metadata refresh in that sense, because the timestamping and such cannot be done with those short messages, right? So yeah, the setup should be frequently repeated for the receivers. And the other question is about, okay, how can we collaborate with ADSC, in particular the business model for collaboration, right? So yeah, this was recently asked to our director, so I will just quote a bit. There are other questions. Let's go with this one first. So, right, so there are multiple ways, right? We can build relations and collaborate. So maybe the easiest and the cheapest, right, way is to communicate and exchange ideas. So find out what it is that ADSC is doing and see if you are interested in that particular thing. So, you know, this is the knowledge transfer piece, right? So most of our projects are already structured and planned, but if the research scope fits into the TSCP project, then we could do something in that space jointly with our partners, so industrial partners or academic partners. So far, the things I mentioned do not involve money, but there is the option where someone wants to, of course, adopt and say license one of our technologies, right? So ADSC is now working on the legal ground to allow that kind of thing. But if there is a particular problem or area that a company would like ADSC to work on, then we value interaction like we caricatured today in the beginning of the talk, right? So it is usually interesting for ADSC staff, especially if we can publish these results, right? I mean, we do not engage with people that have money only because they have money, right? It's important that we succeed in an academic sense. And then we can, of course, prepare a proposal and look for grants together, and that are also targeting to support the field that the said research will be on. So yeah, I think this sums up the common models, but for more details or any questions in that matter, please feel free to contact me. So let me see. Right. So this is my email address. You can also contact any of us, but I mean, given that I am the coordinator for collaboration, maybe I may be the best target. Okay, so let me read other questions. Okay, I have a question about future research collaboration between SUTD and ADSC. We are already in touch with many groups from SUTD, given that it's our partner. So you can just touch us, or you can find us through iTrust, or you can directly contact us. Okay, can you comment on where you see the main obstacles to adoption of the technology you develop, users, equipment, manufacturers? Okay, which technology? But in general, yes. So the main obstacle in terms of adoption is the value given to security and its cost. So once they match, it's usually adopted and required by the companies. And especially the standards, right? The more such technologies are required by the standards, the more public adoption follows. Yeah, this I know this is a vague answer, but if anyone wants to take, for instance, I guess Yao can.
I can add in some.
Yes, please.
Thanks, Adam. So, so based on some of my current practice, I think both could be, but it depends on how totally depends on the way we develop or we spread out the technology. So for example, when we collaborate with the local industry companies and they want to like either license or adopt some of the technology we have developed in ADSC to their product or to their market, then mostly the collaboration between ADSC and the industry collaborator is quite good. But again, what we are designing here is, or what we are developing here is quite research oriented. And as long as we can convert it, more smooth or compatible way to the products, there's no issue here. But mostly for the users, we don't have, or we are not going to help our collaborator to develop that part. So that can be an issue. But for the other point, which is the equipment manufacturers, I think it's not an issue, because during the development of the technology, some of the we may have some specific focuses, and those could be addressed during that. I'm not sure if my answer could suit for this question, but
these are rather delicate things. So yeah, the answer can be a bit vague, I guess, but we can discuss further per technology if you are also working in any of the same fields. Lim, yeah. Let me see, I guess, yeah. I guess that will be all for the questions. So maybe we stay around a bit for a few more minutes in case there is another question, then we can say goodbye. Yeah, I guess that's it. So thank you very much, Benjamin, for organizing all of this and giving us the opportunity to meet. And see you again.
Okay. Thank you, Artem.
Thank you,
Benjamin.
bye. Thank you, Benjamin. Bye.
Very much.
Thank
Thanks,
you
everyone.
for listening, everyone.
Bye.